Hi everybody, and welcome back to Digital Integrated Circuits. I'm Professor Adam Teman of the NICS Labs at Bar-Ilan University, and today we'll be going over the Kahoot for Lecture 9, Memory Peripherals. So we have 10 questions, and the first one is a warm-up. How many 32-bit words are there in a 1 megabyte SRAM? Would it be 1 million, 32,000, 32 million, or 256,000? Well, I'm going to go for 256,000. Let's go back to our slides and remember our memory architecture. So a memory size, or at least the way I've defined it to kind of make the letters seem like something that makes sense, we have W words, and each of these words is C bits. Okay, so in total we have W times C bits in the memory. The address bus, which would be A bits, means that 2 to the power of A equals W. So in our question from before, what we had, and I'll go for a new slide for this, is that we had a 1 megabyte memory. Okay, sometimes we write MIB. A 1 megabyte memory means we have 2 to the power of 20, that's 1 mega. Okay, and multiply that by 2 to the 3, that's 1 byte. Okay, that gives us 2 to the power of 23 bytes. And we asked here how many words are there that are 32 bits. So 32 bits equals 2 to the power of 5 bits. So when we want to ask how many words there are, we will take 2 to the power of 23, divide it by 2 to the power of 5, and we reach 2 to the power of 18. Well, that is the same as saying 2 to the power of 10 times 2 to the power of 8. 2 to the power of 10 is 1 kilo, or 1,000, and 2 to the power of 8 is 256. So that means we have approximately 256,000 bits. Okay, 1,000 words, excuse me. So the answer to that was 256,000. For our next question, assuming that the 1 megabyte memory is byte addressable, how wide is the address bus? Is it going to be 8 bits, 16 bits, 18 bits, or 20 bits? So byte addressable means that we can address each byte separately. Similar to saying that the words are byte long, but usually we differentiate between if we can address subwords, which in this case are going to be bytes. So of course it's going to be 20 bits. Just going back to our type of a decision over here, this was actually an easy question. So remember that we have a 1 megabyte memory, and we want to make it byte addressable. That means we need to be able to address 1 mega addresses, and that's going to be 2 to the power of 20 different addresses, and therefore we need 20 signal bits. Okay, so it was actually a pretty easy question. Just because it's a megabyte memory, we need 20 addressable bits. Question I ask, for the 1 megabyte memory, but this time with 32-bit words and MUX2, in other words, we have 4 words per row, how many address bits feed the row decoder? So is it going to be 8, 10, 16, or 20? And I'll give you a moment to try and figure that out. And the answer is going to be 16. So again, the question is, for 1 megabyte memory with 32-bit words and MUX2, how many address bits feed the decoder? So going back to this over here, our multiplexing factor M, okay, is going to be the number of words in a row. So we have 2 to the power of M words in a row. If our multiplexing factor for MUX2 equals 2, that means we have 4 words in a row. So we're going to be folding the words, and so therefore we're going to have 4 words in a row. So let's see how we figure this out. So if we have 4 times 32 bits in a row, that's going to be 128 bits per row, or 2 to the power of 7. If we have a total of 2 to the power of 23 bits, as we saw before, divided by 2 to the power of 7, that's going to be equal to 2 to the power of 16, and therefore we're going to have 16 address bits, 16 bits of the address signal going into the row. So we have 16 bits over here. So enough with kind of figuring out the sizes and so forth of SRAMs, and we'll go into a different question. What is memory read access time? So is it the number of cycles it takes to achieve a read from the memory? Is it the time it takes from the clock edge until the read value is stable? Is it the address setup time plus the time for the read value to become stable? Or is it the time from read enable until the read value is stable? And of course, the answer is the time it takes from the clock edge until the read value is stable. So let's take a look at that. Okay, so this is a type of timing diagram you would expect to see for a single cycle latency read and write SRAM. So what we're going to have is we're going to have setup and hold definitions for each of the input signals with regard to the clock. So once we have, a rising edge of the clock, for instance here, we're going to have some setup time and some hold time. So this is going to be T setup, and this is going to be T hold, that our data has to be stable before and after the clock edge. And that's going to be true for the address bits, for the data bits, and for the read enable, write enable, which are often just a write enable. Low will be to write and high will be to read. So those are taken care of by this setup and hold constraint, but they're not what actually reads out of the memory or decides on how long it takes to write the data that's waiting there for the memory, because these have to be ready and stable well before the clock rises. On the other hand, when we have a read cycle, so we raised the write enable, which is a low write enable, so the high state is going to be a read enable. That happens again long time before the clock changes, and we provide an address again a long time before the clock rising edge, at least setup time before. But then we get the clock rising edge, and there is going to be some amount of time after the clock edge until the data that's coming out is going to be stable, and that is going to be our access time. So it's similar to a TCQ of a flip-flop, but we're going to call it access time. I just want to note that access time on a type of a macro like this is not necessarily a good enough measure for the performance of the macro, because we can add some delays and so forth, some sort of skew internal into the macro, and make this access time shorter. But that will increase our setup time. We'll have to provide the data much earlier. So usually a kind of a good way to assess the performance or the real delay that the memory will take will be the setup plus the access time. But the definition of access time is in regards to the next path that's after the SRAM when we read out, and that's going to be from the clock edge to the time the data is stable on the output. So that was our answer over here, and the other ones are not true. We do call this a single cycle single cycle latency SRAM, and that's the number of cycles it takes to achieve a read, but that is not the definition of read access time. Of course, it also depends, that would be very dependent on the clock frequency, and we just say it has to work in one cycle, regardless of the frequency. Okay, and this is what I said, address setup time plus the time for the read value. That may be a good way to evaluate the kind of total delay of the SRAM, but it is by no means the access time. The time from read enable until the read value is stable, again, that's similar to setup time. The read enable has to be stable well before, or at least setup time before the clock edge. So it has nothing to do with when the read value is stable. That is triggered only by the rising edge of the clock. Question number 5. What is the row number of the word line Boolean function shown below? Okay, so we have this function here, A7 bar, A6, A5, A4 bar, A3 bar, A2, A1 bar, A0 bar. And I'll give you some time to look at that. Which word line? What is XXX over here? Is it 128? Is it 64 hexa? Is it 9B hexa? Or is it 99? And before the clock ends, I will answer that it is going to be 64 hexa. So I want to go back to our slides, and we see over here that what a decoder actually does. And this is, you probably remember from some sort of early digital system Boolean algebra type of a course, that if we want to define what the function is that will actually turn on our word line, we can give the binary equivalent of it in with bar representing a 0 and a non-bar representing a 1. So for example, this would be 0, 0, 0, 0, 0, 0, 0, 0, which is obviously word line 0. And this one would be 1, 1, 1, 1, 1, 1, 1, 1. Well, so many ones is actually a pretty hard number to discuss and say what it is. So what we will actually do is we will discuss it in hexa because it's easy to go between binary and hexa. So we'll take 4 of the bits, we'll separate between them, and we'll just look at each partition of 4 bits separately. And in hexa, 1111 is F. Okay, so we could call it OXF. And 1111 is OXF. So this is going to be equal to OXFF, and that is equal to 255, as we see over here. Well, in the example we had, we can look back at our Kahoot, and we had A7 bar, A6, A5, A4 bar, A3 bar, A2, A1 bar, A0 bar. So that's going to be 0, 1, 1, 0, 1, 0, 1, 1. So we're going to have 0, 1, 1, 0, 0, 0, 1, 1. Was that what it was? 0, 1, 0, 0. So we're going to put the partition in between them. And what we can see here is 0, 1, 0, 0 is, of course, 4 in hexa, OX4. And 0, 1, 1, 0 is going to be 6 in hexa, OX6. So that's going to be equal to OX64. And that is the answer in the Kahoot. Question number 6. What is the branching effort of a 6 to 64 row decoder? Is it going to be 6? Is it going to be 32? Is it going to be 64? Or is it going to be 128? So if the previous questions had maybe a bit of a harder calculation, this one is pretty easy. It's a straightforward 32. And to get to that answer, let's just go back to our problem setup for the logical effort of the decoder. And what we could see here is that what we have in a decoder is we have each word line has to be driven by some sort of a post-decoding cell or some sort of an AND gate that is a function of all of the address inputs. And we can see here that we have to have one word line for each. So for example, there's 256 bits, there are going to be 256 of these word lines. So the number of word lines or the number of AND gates over here is going to be exactly equal to the number of rows. I mean, that's something trivial, but sometimes it can be confusing for some students. And then what we have here is the AND gates are going to be, each one of them, one of these functions, in this case of 8 bits. And for example, for the first one, if we look at A0, A0 for the first one is going to be 0, and A1 is going to be 1, or actually A0 bar and A0. And for the next two, again, we're going to have, for the next one over here, we're going to have, again, A0 bar, and the next one is going to be A0. So we can see that exactly half of these will get A0, and exactly half of them will get A0 bar. And because we're talking about binary things, we know that exactly half of the rows will get A0, and exactly half of AI, and half of them will get AI bar. So for each of the AIs and each of the AI bars, we're going to have a branching effort of exactly half the number of rows. So therefore, the answer is quite straightforward. It's going to be half the number of rows. And in our case, when we have a 6 to 64 row decoder, the row decoder is going to drive 64 word lines at the output. Okay, so we have a 64 output. That means the branching effort is going to be half of that, which is 32. Question number 7. For a 512 row array, what is the size of the predecoders if we want 3 input NAND post decoders? So, is it going to be 2 to 4 decoders, 3 to 8 decoders, 4 to 16 decoders, or 2 2 to 4 decoders, and 1 3 to 8 decoders? I'll give you a few seconds to think about that. And the answer is going to be 3 to 8 decoders. Again, let's go back and show how we figure this thing out. Again, what we have here is we're going to have, our post decoders over here. We're going to have 1 per each word line. Okay, and these guys are going to get inputs of some sort, and I just defined in the question that these have to have 3 inputs each. They're going to be 3 input AND gates. Well, what 3 input AND gates means is that we're going to have some bus of data that this is going to be connected to, another bus of data, and this is a certain number of bits, that this is going to be connected to, and another bus of data that this is going to be connected to. Okay, and the same will be for this one here. Okay, this is going to be connected to one of these bits, this is going to be connected to one of these bits, this is going to be connected to one of these bits, and so forth. Where do these buses come from? They are actually the outputs of decoders. So we're going to have, these are the predecoders. There are going to be 3 predecoders because we defined that the postdecoders are going to have a fan-in of 3. So we're going to have to tap one of the signals coming out of one decoder, another from the other decoder, and another from the other decoder. Well, remember here that we defined before that this is going to be a 512 512 rows, which equals to 2 to the power of 9. That means we have exactly 9 address bits. So there are going to be 9 address bits coming into this predecoder. So if we want to do it best and the most predecoding possible, what we can do is we can just easily split this into 3, okay, and give 3 bits here, 3 bits here, 3 bits here. So if these decoders have 3 bits at the input, then they obviously have 2 to the power of 3 or 8 bits at the output. Okay, so we're going to have 3 to 8 decoders. And just as a hint for the next time, what we have to make sure is that the number of address bits over here, right? The number of rows, log 2 of the number of rows, has to be equal to the sum of the inputs to all the decoders. Again, this input of 9 bits had to be distributed between these 3 decoders in a mutually exclusive way. So 3 plus 3 plus 3 equals 9, and so that's how it's going to work for these 3 decoders. Of course, we could have done something like 2, 2, 2, and 3, or something like that, but then we would have had 4 decoders over here instead of 3. So our answer is going to be 3 to 8 decoders. So question number 8. For a 1024 row decoder, what is probably the most recommended predecoding configuration? Is it 5 2 to 4 predecoders, 2 3 to 8, and 1 4 to 16 predecoder, 2 4 to 16 and 1 2 to 4 predecoder, 2 5 to 32 predecoder? Well, I'm going to go for the last option, 2 5 to 32 predecoder. Let's go and see exactly why. We said that for predecoding, we should actually usually do as much predecoding as possible. And what does that mean? We should use the largest predecoders that we can get. So in this example, if we have 8 bits, we can divide them into 4, 2 to 4 predecoders, or 2 4 to 16 predecoders. And what I wanted to say is, at least for 3 reasons, we should go for the 2 4 to 16 predecoders, have as large predecoders as possible. So why is that? Well, for one thing, we get a 2-input, NAND gate that's driving the word lines over here versus a 4-input NAND gate that's driving the word lines over here. Remember that we have an SRAM array over here, and we have these thin cells that are sitting here that we saw in the last lecture. And what we have to do is really put, this NAND gate over next to these cells. We can sometimes, have a double height and then put 2 of them next to each other and have one go to the first row and one go to the second. But really, we would like to pitch fit as much as possible. And taking this NAND gate, it will be probably pretty easy to get, 2 lines here along 2 inputs along with VDD and ground, and then 1 output out of it. But getting 4 inputs into here may be a little tricky, especially with the very reduced height of the SRAM over here. So for that reason, we want to have better pitch fitting using a 2-input NAND gate versus a bigger 4-input or 3-input NAND gate. That's number 1. The second thing is switching capacitance. So for this case, for example, if we go from line 0 0 0 0, we're going to have line 0 here and 0 here and 0 here and 0 here going to all be turned on. And we're going to move to, say, line 1 1 1 1, or whatever, FF, right, 1 1 1 1 1. We're going to have F over here, or I guess it's 1 1 over here, and 1 1 over here, and 1 1 over here, and 1 1 over here. Those are completely different lines. So we're going to have to, discharge these 4 guys, and we're going to have to charge, the other 4. And that's going to be 4 big, long capacitive lines. These have big capacitors hanging off of them that are going to have to be switched. On the other hand, when we have these 2 predecoders, these big lines which have a similar type of capacitance, maybe it'll be bigger because they have maybe a larger fan out or something like that, but they're still going to have this large capacitor that's going to be in the same order of magnitude as this one. We're only going to have to switch 2 of these in the worst case. So that's another reason, because it's going to be lower power. And finally, the number of stages before the large capacitor. So as I said, I have this large capacitor and I'm going to need to drive it with a load. Well, what exactly is one of these decoders? It's just 4 AND gates, that are going to get, a 2 to 4 decoder, right? We have 2 inputs, 2 inputs. Is this decoder. It's going to be hard to put a lot of stages in here. Maybe we can put an inverter or something like that, but it's going to be hard to put more stages. On the other hand, with a bigger decoder like a 4 to 16 decoder, we can break it down into several stages and provide logical effort to drive this large load at the output. So we're going to want to do pretty much as much pre-decoding as possible. And back to the answer to our Kahoot, we really saw that 2 5 to 32 predecoders are probably the best solution. Note that what we have to make sure, though, that we can use the other configurations. For example, 2 3 to 8 and 1 4 to 16 predecoder, we have exactly 6 input signals, 2 times 3 plus 4, that's 10 input signals. That is going to be equivalent to a predecoder for 1024 bit row decoder, 10 input bits. However, these are not balanced, right? This is a 3 to 8 predecoder and a 4 to 16 predecoder, so we kind of have to, I guess, look at the worst case, building up our driver and so forth. I mean, it's not balanced. It's an okay solution, but really the 2 5 32 predecoders is probably a much cleaner solution to go with. And our final question is, what is shown in the picture? And sorry, maybe this isn't our final question. We have one more. Is this a dynamic NAND decoder? Is it a dynamic NOR decoder, a pseudo NMOS decoder, or a column MOS? And we saw this in the lecture. It's actually going to be a dynamic NAND decoder. Okay, so let's go back to this guy. And what we see here is we have what we call a NOR decoder. And why is it called a NOR decoder? And this is a dynamic NOR decoder because we have a pre-charge device and then we have discharge devices. And we can see that on this line, for example, we have hanging off of it one NMOS that's tied to ground and another NMOS that's tied to ground. And that's very similar to showing that we have, a pre-charge device, say this is connected to a clock, and then we have 2 of these pull-down devices which are connected to ground, and that is a NOR configuration. Okay. On the other hand, we could have the other way, where here is our pre-charge device, and then we have one NMOS and another NMOS, and that is similar to a similar configuration over here, where this would be the clock, and here we would have these 2 transistors and the connection to ground here, and this is a NAND configuration. Of course, what I showed you in the Kahoot over there was this NAND configuration. One thing that I can say is that this has a long serial connection, which is going to have high resistivity, so it's not that good, versus here we only are going to have one device in the pull down, which is going to be much faster. However, due to the fact that we have to have an actual connection to ground for each of these guys, often the NOR decoder comes out bigger than the NAND decoder, where we can share the diffusions over here and not have these connections to ground. So a NAND decoder, or we will see later on that things like a NAND configuration in Flash are often higher density, and so they are very popular. But for the dynamic decoder, probably a NOR configuration would usually be best off, because you may not be as tightly constrained for area. Okay, and now we will go to our last question. What is shown in the picture? What we see here is it a 4-to-1 tree decoder. Pay attention, we have 4 bits, A0 to A3. A dynamic column multiplexer. A combined PTL and tree decoder, or a 4-bit synth. Well, of course, it's going to be a combined PTL and tree decoder. And let me just show that over here. So what we saw in the lecture is that our kind of straightforward approach to building a column multiplexer is to take a decoder. This is going to be a decoder, okay? And we put in our address bits, in this case 2 bits, and take out 4. And each one of these they're going to be mutually exclusive, so we're only going to turn on one at a time because it's a decoder. And therefore we can drive the bit lines into some sort of a pass gate. Usually it's going to be a complementary pass gate with a PMOS as well, and only one of them will actually pass the output. So we're going to have this wired type of a multiplexer. The other option to do it, which actually will save transistors because this decoder may be quite large, is to build a tree decoder. In this case, we are going to have several levels. So the first pair of bits, A0 and A0 bar, are going to be connected to a pair of transistors which are going to select between the 0 and the 1, or the even and odd bits, and between the bit line 2 and 3, the even and odd bits. Then these will go into a second level, which are going to be connected to the next bit, which is going to select between, the first pair of these and the second pair of these. And so it's a tree configuration, like a binary tree, that's going to select this down to the bottom. Obviously, this only has one transistor in series, and this will have 2, or log n transistors in series, and so this is going to be slower but fewer transistors than this. But what is often done is we can combine the two, so we can use some combination of this pass transistor logic type of a decoder with a tree multiplexer. So that was what was shown. That is the end of our Kahoot for now, and I will be happy to answer any questions that you ask me on the YouTube channel. Thank you.